Remember that feeling you got when you first saw everything everywhere all at once? Like when your brain was trying to process, hold on, are there multiple Michelle Yeohs running around?
Yeah, the multiverse is definitely having a bit of a moment.
It really is. This deep dive is for anyone who's ever seen those movies and wondered if any of those mind-bending ideas are even remotely scientific.
Right, like, can we even talk about a multiverse and be scientific about it?
Exactly. That's what we're tackling here. How do scientists even begin to think about something as massive and potentially unprovable as the multiverse? We're diving into a paper by Carroll called Beyond Falsifiability, Normal Science in a Multiverse.
Okay, beyond falsifiability. Interesting.
Yeah, because he's arguing that the multiverse isn't some wild, untestable idea, but something we can think about scientifically.
That's a pretty bold claim.
It is. So buckle up, everyone, because we're about to explore the boundaries of what we can know about our universe and maybe even beyond.
And just to clarify, when we say multiverse, we're not talking about infinite copies of yourself out there.
Oh, thank goodness.
Uh,
At least my wardrobe malfunctions wouldn't be infinite.
right, no need to worry about that.
Yeah.
Carol's talking about something much grander. Different regions of space, far beyond what we can observe.
Okay, so like way, way out there.
Way out there, where the fundamental laws of physics, the very fabric of reality, could be different.
Whoa.
Imagine a place where gravity works differently or where entirely new forces are in play.
Okay, pause right there. That's where my brain starts to short circuit. Because if we can't even see these other regions, how can we say anything scientific about them? It feels a little like we've wandered into, like, the philosophy section of the bookstore.
You've hit on a crucial point. It's the age-old demarcation problem. What counts as legitimate science and what's just speculation? It's a question philosophers and scientists have been grappling with for centuries.
Right, like trying to draw a line in the cosmic sand. So how does the multiverse fit into all of this?
Well, Carroll argues that the multiverse, while mind-boggling, can still be approached scientifically. He starts by tackling a common misconception about science, that it's only about making testable predictions.
Right, the idea of falsifiability. Like, if I drop this apple and it doesn't fall down, then gravity is wrong.
Exactly. And if you can't design an experiment to prove or disprove something, then it's not real science. Or so the thinking goes.
Which seems like a problem for a concept like the multiverse.
It does. But Carroll points out that while falsifiability is a good starting point, it's not the whole story. The history of science is full of examples where our understanding evolved in a more nuanced way.
So it's not always about proving something wrong, but about finding the best explanation.
Sometimes.
That's where things get interesting. Give us a for instance.
Let's take the discovery of Neptune. Astronomers noticed that Uranus, way out there, wasn't quite moving the way Newton's laws of gravity predicted.
Uh-oh, cosmic traffic violation.
Basically. Now, did they immediately throw out Newton's laws, this cornerstone of physics?
Like they'd give up their physics street cred that easily. I don't think so.
Exactly. Instead, they thought, what if there's something else out there, something we haven't accounted for?
Some unseen force messing with Uranus.
They hypothesized that another planet, hidden from view, was subtly tugging on Uranus with its gravity. They calculated where this phantom planet should be, pointed their telescopes, and boom, Neptune popped into view.
So sometimes a little cosmic detective work can lead to a big discovery.
Exactly, and that's a key part of what makes this whole multiverse discussion so fascinating.
So instead of just ditching a whole theory when things get a little weird, sometimes you need to dig a little deeper, look around the back, see what's going on.
Yeah, sometimes you gotta look for that other sock.
Haha, exactly. And that kind of highlights how science often progresses, right? Like refining our understanding layer by layer.
It's true. Sometimes a weird observation, like that wonky orbit of Uranus, it leads to tweaking the existing theory. But other times, it signals a much bigger shift is needed.
Ooh, okay, I'm ready for another cosmic plot twist. Hit me.
All right, let's talk about Mercury then.
Mercury, the planet closest to the sun.
That's the one. See, Mercury's orbit also had a few quirks that Newton's laws couldn't quite explain. It was a tiny difference, but enough to send physicists back to their chalkboards, scratching their heads.
A cosmic puzzle.
You could say that. And this time, a hidden planet wasn't the answer. It required a whole new understanding of gravity itself.
Enter Einstein, physics rock star. Didn't he shake things up with his theory of general relativity?
He did indeed. It's like Newton's laws were the catchy pop song, and then Einstein comes along with the full symphony orchestra, adding layers of complexity and nuance.
Okay, I love that analogy.
Einstein's theory, It provided a deeper, more accurate picture of how gravity works, and all of a sudden, Mercury's orbital quirks, they made sense.
So it's about being willing to let go of old ideas and embrace new possibilities, following the evidence wherever it leads, right? So how does this apply to the multiverse?
Right.
Just because we can't hop in a spaceship and go visit other universes doesn't mean we should just dismiss the idea entirely.
Exactly. It's about looking at what we can observe, the features of our universe, the things we can measure, and then asking ourselves, what explanation makes the most sense of all this? What fits the data better than anything else we can come up with? And that's where the idea of abduction comes in.
Abduction, like solving mysteries with Sherlock Holmes.
Haha, you're on the right track. But in this context, abduction just means finding the best explanation for the evidence. It's about weighing different possibilities, considering their likelihood, and seeing how well they fit with everything else we know. And you actually use abduction all the time in your everyday life.
Really? I wouldn't say I'm out there solving cosmic mysteries every day.
Think about it. Like, remember that time you found your keys in the fridge?
Maybe.
You probably didn't assume a thief broke in, swapped your keys with a bag of carrots, and then put everything back in your fridge.
Okay, that's a pretty specific scenario, but I get what you're saying. I probably just assumed I'd put them there absent-mindedly while grabbing a snack.
Yeah.
It's the most likely explanation.
Exactly. You used abduction even if you didn't realize it.
Yeah.
You assessed the situation, the evidence keys in the fridge, and arrived at the most plausible explanation.
Okay, I see. So then applying that to the universe, that's where we get to the cosmological constant.
You got it. The cosmological constant, it's one of those concepts that sounds super complex, but it's actually pretty straightforward.
All right, I'm listening. Break it down for me.
It's basically the energy density of empty space itself.
Hold on. Empty space has energy. That doesn't sound right.
It's weird, but that's what our current understanding of physics tells us. And here's the thing. This energy density, this cosmological constant, it's way, way smaller than what our theories predict it should be.
Okay, so it's a cosmic head-scratcher. But how does the multiverse help us solve this?
Well, the multiverse, it offers a possible solution. See, even before we could accurately measure the cosmological constant, physicists, they were debating about why it was so small. Some theories, they tried to make it exactly zero. Nice and neat, right?
Right, scientists love their elegant solutions.
Exactly. But then there's the multiverse option. And that says, well, what if the cosmological constant isn't the same everywhere?
Okay, so different universes, different cosmological constants.
Imagine a vast landscape of universes, each with its own unique laws of physics, its own cosmological constant. And in most of these universes, it might be too large for stars and galaxies to even form.
So no chance for life as we know it.
Right. But in a tiny fraction of those universes, just by chance, it happens to be small enough to allow for everything we see.
So we just happen to be in that Goldilocks universe where the cosmological constant is just right.
Precisely. It's not that we set out to prove the multiverse, but the multiverse, it offers a possible answer to this otherwise really baffling observation. It's like that missing puzzle piece.
So instead of being a problem, this strangely small cosmological constant, it might actually point us towards the multiverse.
Yeah, it could be a clue.
It's like the universe is trying to tell us something. Okay, but Carroll, he also mentioned something called non-empirical confirmation, which is a little confusing. How can something be confirmed if it's not, based on evidence?
It seems like a contradiction, right? But think about it this way. Sometimes our confidence in a theory, it grows not just from doing new experiments or making new observations, but also from deepening our understanding of the theory itself.
So the more we explore a theory, the more we're like, oh, okay, this actually makes sense even if we haven't directly proven it yet.
Yeah, exactly. And a great example is Einstein's prediction about starlight bending around the sun.
Right, because that was a prediction that came out of his theory of general relativity.
Yeah.
It wasn't like he observed starlight bending and then came up with the theory.
Exactly. Einstein, he's doing the math, working through the equations of general relativity, and the theory is basically like, hey, if I'm right, starlight should bend around massive objects.
And then boom, scientists actually measure this bending during a solar eclipse.
Yeah.
And it's like this amazing confirmation of Einstein's theory.
Right, and it wasn't just new data. It was the fact that the theory had this incredible power to predict things, all based on its internal consistency, its elegance.
Wow, okay, so the theory itself had clues to its own validity.
Exactly, and that's what makes the multiverse even more interesting. While we can't, directly observe other universes, at least not yet. Lots of our best theories about the very early universe, like the theory of inflation, they naturally lead to the possibility of a multiverse.
So we're trying to understand the Big Bang, and suddenly, bam, multiverse.
Pretty much, it's this extra layer of intrigue, right? It's not just some standalone idea. It's potentially a consequence of our best attempts to understand the universe as a whole.
I love those little connections, those aha moments. But even if all of this makes the multiverse seem more likely, what can we actually do with this idea? We're not hopping on a spaceship to go visit other universes anytime soon.
That's the million-dollar question. And it's something Carroll acknowledges, even if we accept the idea of the multiverse, it's not like everything's figured out. Like, for example, there's the measure problem.
Okay, measure problem. That doesn't sound simple.
It's not. Basically, it asks, how do you even begin to think about probabilities when you're dealing with potentially infinite
So
universes?
if we're living in a multiverse with infinite possibilities, how do we even wrap our heads around what's more or less likely to happen?
Right. And while there are a lot of ideas out there for tackling this measure problem, it's still a huge area of ongoing research.
So it sounds like we've been on a wild ride today. We've gone from Michelle Ye to the far reaches of the cosmos to the very nature of scientific thought itself. We've encountered some mind-bending concepts and really wrestled with some of the biggest questions humanity has ever asked.
We have. And while we might not have a definitive answer about the existence of the multiverse like concrete proof, we've definitely gained something valuable. A deeper understanding of how we approach the unknown. We've seen that it's not just about proving things right or wrong, but about carefully considering all the different explanations, looking for the most elegant theories, and always being open to new evidence, even if it means revising what we thought we knew.
It's like we've learned a whole new way of thinking, a new way of looking at the universe and our place in it.
Exactly. And maybe, just maybe, as we keep exploring and refining our theories, we'll find those clues that point us, with even more certainty, to the existence of something truly mind-blowing, the multiverse.
And that is why we deep dive.